to give a bit of context to the viewers, so MIRI is the Machine Intelligence Research Institute. Can you just like give a brief recap on like how long have you been working there and what you do there and what have you been doing before, like past few years?
Yeah, so I work at MIRI. I am a research fellow there. I work on broadly, to sort of very broadly, I think about inner alignment, which is sort of the problem of how do we align the models that we train with the sort of objectives that we're trying to train them on. And I tend to think about this sort of problem from a prosaic perspective, from the perspective of thinking about concrete machine learning systems, also from a theoretical perspective. So trying to think about machine learning systems and understand what they're doing using sort of more theoretical tools and abstract reasoning rather than sort of concrete experiments. So that's sort of broadly what I work on and what I think about.
And yeah, so you're talking about empirical work. So I remember when I first learned about you, it was because I was at a conference in 2018 with Vladimir Mikulik, and it was just after the MIRI Summer Fellows, and you guys were writing the misalignment paper. So it was mostly theoretical, and then I think you worked at OpenAI on theory there, but the whole company was more experiment focused. And also I think maybe before you have some more like software engineer background, so you have like different interests and different expertise in both domains.
Yeah, so I did do a bunch of software engineering stuff before I got into AI safety. The biggest thing that I might be known for in that domain is I wrote a somewhat popular functional programming language called Coconut. And then the first thing I did in AI safety was I did an internship at MIRI, doing sort of more functional programming type theory stuff, but all sort of software engineering. And then sort of went to the MIRI Summer Fellows program, worked with Vlad and other people on the risk neural optimization paper. And then after that, when I graduated, when I finished my undergrad, I went to OpenAI and I did some theoretical research with Paul Cristiano there. And then when that was done, I joined MIRI as a full-time researcher. And that's where I have been for the past year and a bit.
Yeah, for people not familiar with AI alignment, which I think is not the most of the listeners, but like Paul Cristiano is one of the OG in empirical AI alignment research now after Yudkowsky. So like interning with him is pretty high bar, and it's pretty cool to have done. Yeah, it's pretty good to have done that after your undergrad. And yes, so yeah, the library you built was also, you said it was like functional programming, and the stuff at MIRI was also functional programming. So if I remember, so MIRI are one of the leading programmer in functional programming. I think it's mostly on Haskell. Maybe I'm wrong.
Are you talking about Ed Komet?
Yes.
Yep, he works at MIRI.
Yeah,
he's a really big Haskell guy.
And
MIRI does a lot of functional
but Coconut is more like an interpreter or something on top of Python. Like you can do functional programming. It compiles in Python.
Yeah. And then the syntax is a superset of Python 3, and then it compiles to any Python version and also adds lots of functional features and stuff.
When you say it compiles to Python, does it compile to like Python, or does it compile to like PyPy? Like
it compiles to Python source.
Okay, cool. Python source. So is it like very poorly optimized? Like if you need to like put something that converts to Python source, then it should be like super slow, maybe.
No, it's like the same speed as Python, because you just compile it to Python and then you run the Python, right?
But when you're compiling, you're not doing perfect work. But
you don't compile at runtime, right? Like with C, you're not like, well, the speed of C is, well, first you have to compile it, and compiling it takes a really long time. Then you have to link it, and linking it takes a really long time.
Right.
Then you have to run it. You're like, no, the speed of C is you compile it beforehand, and then you check how long it takes to run.
Okay, cool. Yeah, I get it now. Yeah, and I think that's especially interesting to me because I think people like there's a lack in open source, at least in the AI element place. So even if Coconut is not especially for AI element, I think functional programming might be useful for MIRI at some point.
Yeah, it was definitely how I first got into like doing stuff at MIRI, because MIRI was like doing a lot of functional programming stuff, and I had a strong functional programming background, and so they were like, you should come do some stuff here.
Sure, yeah, and I think at some point they were hiring more programmers. I don't know if that's still the case. If they're still hiring more programmers.
Yeah, I think that has changed. I don't know what exactly the current status is. I'm not the person to talk to about that.
Okay, no problem. Yeah, so I guess now your job is mostly writing interesting research on the AI Element forum, sometimes posting it on archive. And yeah, I think your posts are both very precise in terms of vocabulary, terminology, and clear, and also short. So like you can read one and not spend like too long, and then you understood most of the points. So yeah, that's a good thing. Most people don't try to distill what they think about, and you also try to give like concrete proposals for how to solve this. So which is like a kind of a shift I've seen in the past 3 or 4 years, which people having their concrete agendas on how to solve things. So one kind of contrarian view, not contrarian, but like some view you had that was opposite of most of the AI element forum, which is a forum for talking about AI element, is most people were talking about takeoff speeds, like how fast. So to clarify what Paul Crisano meant by fast, what Bostrom meant by fast, slow, takeoff, and then you mentioned something else, which was homogeneous versus heterogeneous takeoff. So maybe you can talk a bit about that, like summarize a bit the blog.
Yeah. So I think, yeah, I'll try to, I think, yeah, so there's a lot of discussion when people talk about takeoff speeds, about fast takeoff versus slow takeoff, continuous takeoff versus discontinuous takeoff.
You can even like summarize takeoff. Like takeoff is maybe a bit poorly defined. So you can even define that if you want. Takeoff
Yeah,
speed.
I think when people talk about AI takeoff, they're sort of talking about, well, at some point we're going to build really powerful AI systems, and then something happens after that. And
Right.
what does that look like? So, do we build the first really powerful AI system, and then it very quickly like dominates the world? It has like a decisive strategic advantage. The only thing that really matters is what that system does. Or we build the first AI system and it's really powerful and transformative, but then also we build another system and we build another system, and there's a lot of different systems that are all sort of existing in the world at the same time.
Like multiple scenarios.
Yeah, so like unipolar versus multipolar.
Yes.
There's a lot of different things you can talk about. So, how quickly do the AI systems get better? Are there sort of big discontinuities in how they get better? How concentrated is the sort of is power over these systems, et cetera, et cetera. So yeah, so one thing that I have sort of talked about in the past in this regard is this homogeneity idea, which is, I guess, in my eyes, the axis that I care about most. It feels like the most relevant, and also the one that I feel like more confident in, and like I can make more definitive statements about. Where homogeneity is saying a homogeneous takeoff is one where all of the AIs are basically equivalently aligned, and a sort of inhomogeneous takeoff is one where we have a bunch of different AIs that are sort of varying degrees of aligned.
Right.
So there's a lot of different things that happen in these different situations. And there's also sort of other aspects of homogeneity. So by default, I sort of mean alignment, but also we can talk about sort of homogeneity of other aspects of how the AIs are built. So I expect quite a lot of homogeneity, I think, by default. I expect to sort of be in a situation where we have a lot of different AIs running around, but all of those AIs are basically all just kind of copies of each other, or like very similar.
Yes.
or in a situation where we just have like a very small number of AIs, but they're still just like, even if you have only one AI, then it's sort of homogeneous by definition.
Yeah, very homogeneous.
And so I think this is like, in some sense, the more important dimension. So I think a lot of times when people talk about sort of this sort of, really fast takeoff scenario means that we have to get that first AI system totally correct. Because if we don't get the first AI system totally correct, in a really fast takeoff scenario, it very quickly controls all of the resources, and sort of only thing that matters is that system. Whereas in a sort of slow takeoff scenario, we get the one system, but then there's a lot of other systems that are competing for power and resources, and we sort of have the opportunity to intervene and sort of control things more as it sort of continues to develop. And my take is something like, I don't think even in the second scenario that we actually have the ability to really do much, even if there's lots of different AI systems running around competing for resources, after the point at which we build the first powerful advanced AI system, given that I expect all of those other AI systems to basically just be copies of the first system. Right. Because if they're all just kind of copies of each other, then what really matters is, did we align that first system properly? And so do we have a bunch of systems running around that are all basically aligned, or do we have a bunch of systems running around that are all basically misaligned? And so therefore, I'm like, well, if you believe in homogeneity, then that basically means you have to believe that the sort of first powerful advanced AI system that we build is really important and critical, and like aligning it is the most important thing, regardless of whether you believe we're actually going to end up in a very fast takeoff scenario. And so then there's the question of, why do I believe in homogeneity? So I think basically I believe in homogeneity for a couple of reasons. First is that I think I expect pretty strongly that we'll be in a regime where the cost of training your AI is just like much, much, much higher than the cost of running it. And this creates a bunch of sort of particular economic incentives. So like one thing that it does is it means that you would generally rather use somebody else's AI whenever possible than have to train your own one. And also in the situations where you do have to train your own AI, because let's say, for example, you don't want to use your like geopolitical rivals AI or whatever, then you're probably going to do so very conservatively. Like if you have to spend $1 trillion to train your like one AI system, just because you don't want to use their AI system because you don't trust, like, I don't know, you're like the US and you don't trust China's AI or something, then like you're going to spend that $1 trillion pretty conservatively. You're just going to be like, well, we basically kind of know what they did. Let's just do the same thing because we really don't want to spend $1 trillion and have it not work. So in this sort of regime, I expect, and then there's some other assumption here, which is like, well, I think basically if you're like running essentially the same training procedure, then like you get essentially the same degree of alignment. And the like really small fiddly details are not what sort of contributes very much to like whether your thing is aligned. It's mostly like, did you basically get the incentives and biases right or not?
Right. So I guess your example with the US and China would be something like GPT-3 being like taking 5 million or something, or 20 million to train, maybe much more to like pay the salaries and like all the experiments that went beforehand. And you don't want to spend like that. This is like relatively cheap for a government now. But if you're talking about billions of dollars, then maybe it's like more expensive, or trillions for like an entire country. So
right. When we get to a point where it's like a substantial fraction of the entire GDP of your country,
yeah,
like you really don't want to like be in a situation where it's like, we're going to spend 1% of our GDP, like there's this other country that has already done this, like built a like really powerful AI and has demonstrated that it works in this like particular way. Like let's say they use transformers or whatever. Like you really don't want to then spend 1% of your entire GDP trying to like make it work with LSTMs. Like you're just like, no, they did it with transformers. We're gonna like do the same thing. Like we just want to have our own version of what they did. And so my default expectation is this sort of conservatism, which is like, well, probably people are just going to copy what other people are doing. And so like it really matters what the first thing is that's like super impressive enough that it gets everyone to copy it.
Sure. Yeah. So if we take the example of GPT-3, then they didn't release the weights, and it was super expensive to reproduce. Like according to different sources, Google might have reproduced it pretty fast, but it's not public information. Then there's like Luther AI who tried to reproduce it for months, and after like 6 months or something, they did reproduce something that had somehow similar results. I'm not sure how close it is.
What they're aiming for is basically a reproduction. It's not a like, it's not worth spending all of those resources if you don't already have the evidence that it's like going to succeed.
Sure. Yeah. So they know it's going to succeed. It's a paper that is known to succeed, but at least you have the architecture and you know the outputs, you know the loss, you know what's the expected behavior. But you're surely not sharing the weights and nor the data. So you had to both like scrap the data on the internet and then get the like
But
source
still,
code.
the data collection procedure was pretty similar, right? Like we're just like, well, the data collection procedure, the basic data collection procedure is we're just going to scrape a bunch of like a large, swath of internet data. Maybe they didn't explicitly release the data, but I think that like, I guess my take is that if you have essentially the same data collection procedure, you have like essentially the same architecture, you like have essentially the same training process, then like you're basically going to get the same alignment properties out the other end. And some people would disagree with that. And we can talk about like why or why not. But
yeah, I think I broadly agree with that. I might just be pointing at like maybe in the future when we get closer and closer to some kind of human level AI, then maybe people might share less of their research about like how they collect the data and stuff. And we just have like super hard to replicate results because we don't even have the architecture or something. We just have the output or yeah, I'm not sure if like the OpenAI in 2025 or 2030 will actually share everything with the other companies, and how long it will take to reproduce it might be like will depend, might be like a big enough gap that they can have a comparative advantage that leads to like them to lead the rate or something.
It's hard to keep your just like basic method secret. I think, so currently, most of these companies don't even try, right? Like, like you were saying, OpenAI just publishes papers on exactly what they did. And they don't give you the weights, but they publish the paper saying what they did. Same thing with DeepMind, Google, basically. I think a part of the reason for this is that even if you wanted to keep it secret, it's pretty hard to keep just like these very general ideas secret because like one person leaves and then like, they can explain the general ideas. They don't need to steal anything from you. It's just like they already have the ideas. The idea is very general and sort of simple.
The moment you hear about it, it's like the moment we heard about like when GPT-3 became mainstream, let's say July, like it was released in some kind of maybe May, maybe they have the results maybe in January or something, and they had some close results, and then they had to like make it better, like improve it for publishing to NeurIPS or something. For DALL-E, maybe they knew about multimodal for a while, and at DeepMind, I think the politics is that they hold up like their private research, a bunch of projects going on for like months, and then they try to publish it to like Nature Neuroscience or like Nature. And so you have like all those like deadlines for papers where they have those 6 months advantage or maybe a year advantage where they all have private information that they don't share to other companies.
Yeah, there's definitely a delay. But like at the point where you have this really powerful system and you start doing things with it such that other people start wanting to build their own really powerful systems, I expect convergence. People are
convergence of people sharing stuff.
Well, people are going to figure out what you're doing, even if you don't try to share things. Like it's just too hard to keep it secret when you're like having this big model and you're out and you're doing all of this stuff. People are going to figure out like what the basic process was that you did.
Like reverse engineering or like social hacking, like people
like you just need one person to basically describe the idea. Like honestly, I expect it's like so insecure with like, I don't know, like can you imagine trying to keep the basic idea of like we used attention secret? Like it's not going to happen.
Yeah, we use a transformer, but please don't tell anyone.
Like you can totally, I think it's totally practical to like keep your weights secret, because if somebody wants to steal your weights, they have to like actually, copy them and exfiltrate the data, and like it's clearly illegal, and like, it might still happen. Like I think it's still quite plausible that, you'll have like hacking attempts where people steal your weights or whatever. But like it's at least plausible that you can keep your weights secret. But like there's just no way you're going to keep the like we used attention to do a big language model secret.
I think one example that goes in your direction is DALL-E, which I think so this GitHub account Lucid Rains reproduced DALL-E in a couple of weeks. I think maybe like less than 2 months, something like that. I think like DALL-E was maybe end of December, beginning of January, and Lucid Rains published it in maybe February or something. So for some experiments, like it gets faster and faster to reproduce it. So I was talking to someone else on OpenAI who told me that he expects multiple scenarios to be like kind of the default, because as an entire community, we get better and better at reproducing what the best labs do. So the time between something like GPT-3 and reproduction gets closer over time. And yeah, so I guess one counter argument or question I had about this blog was, you say that the first, like when the first is aligned, then people will copy it, and by default it will be aligned because it's the same kind of the same vibe or same architecture. But imagine the thing that is aligned as like some kind of those laws of robotics, or oh, don't kill people or be aligned with human values and stuff. So if you're trying to be adversarial and trying to like beat the first AI or smartest AI alive, so not implementing those aligned features, you could just like be very adversarial and attack the first one, who will not attack you back because he's like a human aligned, right? I'm not sure if I'm
Well, so
clear.
one thing which you could imagine is a situation where like the first person, the first organization or whatever builds an AI and they like successfully make it aligned, and then somebody else decides to build an AI and like not do the alignment part.
Exactly.
So, like this relies on there being some separability between the alignment parts and the non-alignment parts, which is unclear. I'm not sure if I actually expect there to be this sort of separability. But then also it relies on like you not caring about alignment as like a good desideratum.
Mm-hmm.
But that seems really unlikely. Like alignment is like pretty useful for almost anything you want to use your AI for. Like you would really like your AI to do the things you want it to do. It's like very, it's like not, it doesn't really seem much different than just like, you know, and especially again, like when we're in a situation, which is like what I expect, where these sort of training runs have a truly astronomical cost, right? Where like,
Mm-hmm.
you know, your little research lab in like a university or whatever isn't going to be able to replicate the biggest labs because the things cost like, you know, billions of dollars for a single training run, trillions of dollars or whatever. Then you're in a situation where like you really don't want to risk spending a trillion dollars or whatever and have it not be aligned, have it like not do the thing which you want it to do.
Right. So
And
I guess
so you're going to copy whatever alignment features the other team did that they like successfully demonstrated. And now it might be the case that in fact the first team's thing only looks aligned. Maybe it's not really aligned. You're still going to copy it, I think. And so this is why I sort of have this view, which is like, well, even in a sort of very multipolar, continuous, slow takeoff world, we still basically just care about making sure that the first really powerful system is aligned in the like traditional, conventional way that we think about in the fast, discontinuous takeoff world.
right. So I think what you're mentioning. So one of the posts where you're trying to distinguish between like clarify alignment terms. I think Paul Cristiano tried to clarify it in one of his blogs on Medium, which is alignment is basically having an AI doing what you tell him to do. So very basic terms. And then you distinguish something like impact alignment, and sorry, intent alignment, which is trying to do what the human wants you to do, and then impact alignment, which is not destroying the universe, like not causing harm to humans. Is it essentially correct, or maybe you want to nuance it?
Yeah. So impact alignment is like, in fact, not doing bad things.
Mm-hmm.
Intent alignment is like trying to not do bad things, in my definition. And then we can further split each of these things down. So intent alignment can be split into um, outer alignment, which is like is the objective that it's trained on aligned, and then this objective robustness thing, which is like, is it actually robust according to that objective across sort of different possible situations. And then I don't know, you can the sort of the whole post has this sort of breakdown where it sort of looks at, okay, how can we sort of break down these different ways of sort of thinking about alignment into like different subproblems.
Yeah, I was trying to find the actual picture from the blog post because it's pretty good. But yeah, I think it's in clarifying inner alignment terminology. I was just trying to see if I could make it as a background for fun, but I think it's pretty hard. Let's see. Yeah, so I think so what you were mentioning before is kind of companies would want something like intent alignment, or like something that does what the Chinese government wants them to do. And if the Chinese government wants to kill everyone in the US or like take over the world, then it must be intent aligned in the sense of trying to optimize for like do the same thing that the Chinese government wants them to do. But it doesn't mean that it won't kill um, other countries, right? So um, so when like the second actor might want just to have something useful without it being beneficial for the entire human race.
Yes. So you still have, even if you have like, you solve the sort of like intent alignment style problems, and even if you have a very homogeneous world, you still have situations where you have like standard human coordination problems, where you have to be able to coordinate between, one human organization is trying to, um, fight some other human organization. And then the hope is that human coordination is a problem, like, human organizations fighting other human organizations is a problem that we can mostly solve via like normal social and political dynamics. It's still hard. We did make it through the Cold War without any nuclear bombs being dropped, but it was close.
Right.
Hopefully, if we're in a similar situation, we can make it through something like that again. The like real problem though would be, at least we want the opportunity to be able to do so, right? We want humans to be the ones that are in control of the levers of power, such that it is, even possible for humanity to be able to coordinate to make it through a like similar to the Cold War style situation. But
So
if
you want
humans aren't
humans
even
to have
in
the
control of
tools
the levers
to
of power at
coordinate,
all, then we can't even do that.
right? So it's necessary condition to have a peaceful outcome, not a sufficient one.
Right.
Okay. Yeah, I think that's essentially right. I agree with it. But then I guess some people might say that I think the political problem is maybe the hardest one. And like if we have some kind of very authoritarian regime that I don't know says working on AI is you can go into trouble if you work on AI to advance AI, and like everyone is doing good old like manufacturing job or like agricultural job something, then if we solve the political stuff before and we have some large piece or like large government, then we solve kind of we have more time for AI safety. That's a bit like of the Stillman of the other position.
Yeah, I mean, certainly I think there's lots of ways in which you can approach this problem of just like AI existential risk in general. There are like social and political aspects of things that are worth solving, as well as technical aspects. I think that currently I'm like, well, I feel like most of the existential risk comes from we're just not going to be able to solve the technical problem.
Right. Yeah. Most researchers working on this, I guess, think similar things, which is I think it's pretty tractable. I think the solution that you give in your other blog posts seem pretty tractable, and solving politics or human coordination or fighting against Moloch seems a bit harder. But yeah, so I agree with that. That is worth thinking about it. And yeah. Okay, so I think we covered most of this blog post, and then sure, you had another one that was interesting to me because I worked a bit on AI element research myself. I did some open sourcing as well on Quantilizers, and so that's a bit what I'm familiar with in terms of research. And you worked a post on like how to like Quantilizer. Essentially, if I want to summarize it, would be we try to have AIs that perform in some kind of human way, without it being too bad at the task. So if you have a human demonstrating a task, and the let's say a robotic task or some game playing or feeding another baby or something, you want the AI not to find the optimal action, because the optimal action would kind of hack the game, but you also want it to perform well and not do stupid things. So if the human is like drinking alcohol a tenth of the time of the day, you don't want him to drink. You don't want the AI to drink alcohol. You want the AI to do the normal human stuff in the afternoon. So quantizers is essentially taking those 10% of this quantile of actions that are good, but that are still human-like. So when the AI tries to imitate those actions, then it can like perform. So one thing about quantizers is doing that. I guess there are other ways of seeing quantizers, but this is one way of looking at it. And so in your post, you're kind of talking about what Yudkowsky's how it defines bits of optimization, which is when you have this interval of length 1 of probability mass, then if you have something that is in the half of highest utility, then you're somehow halving the space in half. So you're having 1 bit of optimization or something. And then the closer you get to the optimization power, the more bits of kind of optimization you need. Yeah, maybe you can say that better, nuance it, explain more.
Yeah. So I think you're referring to my post on operationalizing
Exactly.
compatibility with strategy stealing.
Exactly.
Yeah. So in that post, I talk a little bit about optimization power and quantilizers. I give a definition of optimization power in terms of quantilizers. And then I try to relate this to the strategy stealing assumption and value neutrality verification. Maybe the best thing to do will be, so I'm happy to talk a little bit about this post. I think it's interesting. I wrote it. So some things which I think. So yeah, maybe I'll start with strategy stealing. So I think strategy stealing is an interesting thing because I think there's a lot of different ways to think about it. The like very simple thing is that there's this formal result, which is, well, if you have a game and it's like symmetric, we have a bunch of different players and they're all sort of, playing, they have like, access to essentially the same actions and stuff, then you can always just sort of copy the strategies of any other players such that you can never sort of do worse in expectation than if there are n players getting, 1 over n of the sort of total resources.
Okay.
Even if there is like, in any situation, even if there's like as long as it's symmetric, you can sort of make this work. Okay, so what does this mean? Well, so one of the ways in which we can interpret this, and Paul has sort of talked a lot about this, is that we can sort of think about this as giving us a sort of general desideratum for AI safety, because we are currently in a situation where humans sort of control most of the resources. And so we should expect that, by default, that sort of distribution of resources shouldn't change over time, because we can just sort of, if other agents are introduced and they start with very little resources, then we can just sort of steal whatever strategy they have. And, in expectation, we should have the same proportion of total resources that we have right now at any future point in time.
Right.
But then this fails for AI because AI is sort of has this property that it might be systematically biased towards certain values over other values. So for example, values which are very easy to specify, and so we can build reward functions for them really easily, will win out systematically. And so this breaks strategy stealing because now it's no longer symmetric, because some people's values that are easy to specify will like systematically win out. Similarly, values that are really simple, such that they're really easy to find by default in sort of training processes, will sort of systematically win out. And so one way in which you can think about one thing we might want a sort of aligned training process to do is not be sort of systematically better for some of these sorts of values and other values. and in particular, not be systematically better for like, simple or easy to specify things than for like actual human values that we care about. And so one way in which we can define that notion is using sort of this concept of optimization power and asking, to what extent is it applying more optimization power? Is it sort of able to apply more optimization power to some sort of tasks than other tasks? And in particular, if it's able to apply, more optimization power to, I have this example, which is like we consider Sundar Pichai, who is the CEO
Right.
of Google, and he wants a bunch of different things. He wants like to be happy and for his family to be happy, but also he wants Google to make money. And so he has like, a really powerful AI system, and it's like, trying to do what he wants. And so he's like, okay, here's some things I want you to do. I want you to like, find some ways to make Google money, and also, find some ways to like help me, figure out my life, and also like, I also kind of, he probably cares about humanity, and he wants humanity to be in a basically good spot overall, but also he wants Google to make money, obviously. And so, the AI goes out and it tries to do this, but there's like a real problem if the AI just like is much, much, much better at making money for Google than it is at any of these other things.
Right.
Because then it goes out and it's like, well, it makes a bunch of money for Google, and it's really, really good at making money for Google, but it's like very bad at like doing any of these other things. It doesn't really know how to like put the world in a good spot for humanity. It doesn't really know how to make Sundar happy. It doesn't really know how to do any of these other things that Sundar cares about. And so from Sundar's perspective, what ends up happening is that, some of his values lose out to other of his values. And so in the long run, we end up in a situation where we've built AIs that sort of systematically favor the development of and sort of enhancement of certain values. The enhancement of like competition values, like, getting more money for Google at the expense of these other values, like, is the world good? And this is bad. And so we'd like to avoid this.
Right. I think that kind of resonates with how easy it is to like hack the human brain and optimize for like Facebook ads or like TikTok views. And it's harder to specify, make humans happy in the long term. So like we would kind of converge towards easy to hack, brains, behaviors, and maybe like even like optimizing for the crypto market or optimizing for the trading market is something with very little information and like very low dimension compared to like visual inputs. So maybe AI will be good at things that are easy to do now and that are tractable in terms of input space, I guess. But yeah, for Sundar, I think like it's kind of so what you're saying is it's kind of so the value is so AI would converge to what is easy, and if what's easy is maximizing profit, then it will do that instead of other things. But if it understood that what Sundar wanted was actually Google making money to benefit the world and making his life good, and it will not like create some kind of bad Google doing bad for humanity and having Sundar overwork overnights and like not spend time with his family or something. So at some point,
it's unclear, right? If it only like, you can imagine a situation that is just kind of like the current world, but where like we know how to build AI systems that do like very simple tasks that we can specify, but we don't know how to do systems that do really complex, hard to specify tasks. Then like we could very easily end up in a situation where, due to competitive pressure, Sundar is just kind of forced to use these systems and like sacrifice all of these other values to like make sure that Google's able to make money. But like there's just no ability to, because the only powerful actors in the world are these AIs, and like, but they can only be used for these sort of simple tasks. Then you sort of just you're forced competitively to like keep deferring to them and giving them more power and resources to be able to give you more power and resources, but you never get to a point where you can actually use that power and resources for like what you actually care about.
So
to be clear, this isn't the sort of world that I expect by default,
right.
but it's worth sort of pointing out as like in a sort of way of thinking about a particular type of alignment problem that is like not the traditional alignment problem, and like doesn't necessarily isn't necessarily solved even if you solve more sort of other aspects of the alignment problem.
Interesting. So yeah, if you don't solve all the problems, then you might end up here. And I guess the thing is some kind of Google, like I see it as a very powerful Siri or Google Home, where it would be like a good oracle, like Sundar Pichai coming home and like asking his Google Home or something like, yeah, what's the best strategy for tomorrow? I guess somehow it's not that far away. Maybe like strategy wise, running a company like Google is hard, but like chatbots that you can talk to and like has ask for simple decisions. I don't know. Um, okay, so okay, and the link with the kind of optimization thing is that
Mathematically, we can use optimization power to give a definition of this. That's the link.
okay, cool. And I think that's interesting because like in the past, okay, so in the like first two episodes, I had this thing I called Connor's rule, because Connor Leahy, he had other podcasts on like machine learning street talks with Yannick Kilcher and stuff, and they went on defining multiple times intelligence. And so he's kind of the rule is like you shouldn't talk about intelligence, you should talk about optimization, like other stuff that the AI would do, and not like talk about words. So I feel like optimization is a good word. um, and you give a bunch of different useful terminology in the so in risk from learning optimization you kind of introduce mesa optimization like other stuff, and then you clarify it even more in clarifying inner alignment terminology, which is, I don't know if you can see the diagram before behind me, or if it's just in my camera.
It appears to be inverted for me, but I can't see
Oh,
it.
it's inverted for you. Sorry, because it was inverted for me, and then I inverted back. So I need to invert it back. I don't know what the camera will do at the end. I can have both. um, yeah, go ahead. I will just remove that.
Yeah, what do you want me to say?
Yeah, so about like maybe you can start with mesa mesa optimization, and like
Sure.
optimize, like how do you define optimizers, and what's a mesa optimizer?
Yeah, so risk learned optimization does take a sort of stance, which is something like, optimization is the important thing to think about. It's not intelligence or agency or any of these other things. It's like optimization is the key thing, which is similar to sort of what you were describing.
Right.
Certainly, there's a lot of sort of discussion around this stance and whether this is a good stance. I think it is a stance that lets you say a lot of things, because optimization is like a reasonably concrete, coherent phenomenon. And so you can say a lot of stuff about optimization. And this is sort of what risk learned optimization tries to do, is say a bunch of stuff about optimization. Yeah, I can say more. I'm happy to like talk more generally about like what is risk learned optimization basically saying, what is the inner alignment problem, et cetera, et cetera.
Yeah. So I think when useful. Okay, so then so I recently reread the actual introduction. So I think there's like a sequence on AI Element Forum where you define like there's an introduction where you define all those concepts pretty precisely. I feel like optimizer is, maybe you said that already, but it's like searching anything that search over a space to find the best solution according to some objective, and actively search. So, for instance, there was this example from Daniel Phelan about a bottle is cap of a bottle. Is it a cap in English?
A bottle cap.
A bottle cap is a bottle cap an optimizer because it's kind of preventing water to go away. So it's not actually optimizing for anything, but it's something that humans optimize for. Um, and so it's a result of an optimization process from humans. And humans are something evolution optimized for, that we're optimizing for different things, like instrumental things like having sex without making kids, or other things. But and so that's maybe some kind of disagreements I have on your examples. And I think in your podcast with Daniel Phelan in AXRP, you kind of said that it's useful, like it's useful to see humans as optimizing, sorry, searching for some solution that is not directly evolution's function. So in terms of alleles, chromosomes and stuff, because like some humans don't make kids. So my counter argument to that would be that even for humans that don't make kids, they're still like kind of trying to optimize for evolution's pressure in a bad way. So imagine they're, I don't know, very good researchers. They don't care about making kids at all, but they're just very passionate about math. So they will end up producing value for the world with their math papers that will end up in like more, more GDP or more kids in the future for other humans.
Yeah, I think this is not how evolution works though, right? Like, I think it is just actually true that like, if you really let evolution keep running, it would like not select for this sort of behavior. Like, evolution certainly wants some altruism, but it also doesn't want you to like live down the street from a sperm bank and not go there every day, right? Like, that's insane from an evolutionary perspective, regardless of like whatever else you're doing.
But it's still like we're like I still feel like we're trying. So like our instincts, like our primal, like our lizard brain still wants to optimize for evolution. It's just that we're bad at it, or that we've evolved for like building those tribes and society that is a proxy for building more kids. I don't know.
Well, the key word there is proxy. The things that we care about are in fact proxies for what evolution cares about, but they're not the same, right? Like, you can certainly tell lots of stories about, and this is true because there are proxies, right? You can think about, status and power and, sex and all of these things clearly are proxies for, and they're related to in the ancestral environment, the sort of, passing your genes on. But we don't actually care about passing our genes on. At least most of us don't. You know, and I think something like the sperm, do you donate sperm or eggs is a good example of like, most people don't, or they have to be paid to do it, right? And it's like that's evolution would never want that. That's like clearly evolution is like, this is the most important thing you should be doing, right? You got to be doing nothing but that. But from a human perspective, we care about the proxies. We're like, what I care about isn't actually, just like literally are my genes in the next generation. Even like the humans that generally care about like having children usually care about like, I want to be able to raise my children. I want to have a connection with my children.
Right.
Not just like, I literally want more of my DNA in the next generation. Right?
But what about if those proxies are actually good at like making like more humans long term? Like evolution evolved and found this new solution in surf space, which is no, the actual good stuff is not just to be a lot. We actually need to be in some kind of tribes and have social defense to fight dinosaurs or monkeys or something. And then if everyone was spending sperm, would give sperm to sperm bank,
evolution doesn't work on a group level though. It works primarily on an individual level. And so evolution is happy to like evolve to extinction on a group level because it's primarily selecting on an individual level.
But wait, so like if you're selecting genes,
this is why we have things like selfish genes that like that doesn't actually help you. It just like copies itself from like place to place. It's like evolution isn't just selecting for like your sort of like the performance of the whole group, but it's like very explicitly selecting for like your individual performance. Another example of this is like sex ratios. So like in theory, you would like evolution for like the maximum like production of additional children would want like significantly more females in each generation than males. But in fact, what we see is that across species, the sex ratio converges to 50%. And the reason that converges to 50% is that from a selfish individualistic perspective, even if you're in a population where there are greater than 50% females, then you are at an advantage passing on your genes to the next generation if you have a male child. And you're at a disadvantage if you have a female child. And so despite the fact that evolution from a group perspective would rather have a sex ratio that is not 50%, from an individual perspective, it has to converge to 50% because of it's the sort of only stable equilibrium from a sort of selfish individualistic perspective. And evolution primarily selects on the individual.
But then those we kind of converge. So it's like a bunch of individuals with egoistic genes that converge to some Nash equilibrium at the society level.
Well, so we can also certainly talk about why is it that humans are altruistic? Where did that come from evolutionarily? I think that leading theory is something it's good for it's useful for cooperation. Being altruistic is helpful for your ability to cooperate with the rest of the group, because if you care about the rest of the group and they care about you, then you can cooperate really seamlessly with them. And so in some sense, altruism is selfishly useful in this perspective from an evolutionary perspective. It's like evolution would rather have each individual be more altruistic because it helps them work better with the group and be less ostracized by the group, and therefore be more likely for that individual to have more children. And so this is a individualistic story of why, from the perspective of a single individual, evolution would rather that individual be more altruistic.
And what about people being the opposite of altruistic and just taking defecting all the time with altruistic people? Did this would be the more the better position, right?
No, the point that I'm making is that this is not the case.
Okay.
For evolution, for each individual, altruism serves a purpose for helping that specific individual have more children.
Cool. Okay. Cool. Interesting. So yeah, and I think that there are other distinctions you make that are interesting. So so just to define the basic terms again, because I think most of the listeners are not familiar with the paper. So there's what we call evolution. A good analogy for evolution is what we call the base objective of so if we maybe a neural network is an easier example.
I think it's better to start with neural networks. And what risk neural optimization does is it really tries to ground everything. And I think one of the big things that risk neural optimization does that sort of all previous discussion didn't do is really carefully ground everything in machine learning.
Sure, yeah. So let's talk about machine learning. So what's interesting is when we have optimizers like Adam or stochastic gradient descent, then you're trying to change your parameters, theta, so that you can, I don't know, better classify cats and dogs. And at the end of the day, when you change those parameters, at the end, they might end up at inference time doing something like optimization. So if you, for me, the example for me would be something like a recurrent neural net, where you do backprop through time, where you're optimizing, and you're at inference time, you're kind of only using the either I don't know, it's the latent cells or something. Some are frozen and some are not, and then you can adapt to what you get at test time. And I think that was one example of a blog on That's Wrong trying to reproduce MESA optimization. Did you have better examples maybe of sub-optimization?
So the classic example that I like to use to really explain sort of what's going on with risk neural optimization is this maze example.
Right.
So we can imagine a situation where we train a model in a sort of a bunch of small mazes, sort of randomly generated mazes, but they're all kind of small. Mm-hmm. And we put a green arrow at the end of the maze. It gets a picture of the maze, and we put a green arrow at the end to say, this is the end of the maze. We're supposed to go here. And we train a bunch in this environment. And then we deploy to a new environment, which has the following properties. It has larger mazes. the green arrow is no longer at the end. It's at some random location inside of the maze. But we still want the agent to get to the end. We still want the agent to leave the maze. Or you could flip it and you can be like, we still want the agent to go to the green arrow and not go to the end. Either way. The point is there are a bunch of different ways in which this agent can generalize. So here's one generalization, is it just goes to the larger mazes and it doesn't know how to solve them. It just fails to solve big mazes.
Right.
I would sort of call this, it's just, it's sort of capabilities don't generalize. It didn't learn a general purpose maze solving capability. Or it could learn a general purpose maze solving capability. Its capabilities could generalize. And it could learn to go to the end of the maze, which is what we want it to do. And so its objective, going to the end of the maze, also generalizes properly. But then there's another situation, which is its capabilities generalize. It knows how to navigate the maze successfully, but its objective fails to generalize, and it learns to go to the green arrow rather than to go to the end. And then what's scary about this situation is that we now have a situation where we have a very capable model that's learned a general purpose optimization procedure, but it's deploying that optimization procedure for the wrong objective, to get to the wrong goal, not the one we intended, to get to the green arrow instead of what we wanted, which was to go to the end of the maze. And so this is really dangerous because we have a powerful competent model which is directed in a direction we never intended. And what's happening here is that there was this unidentifiability where on the training distribution, we couldn't tell whether what it was really doing was going to the green arrow or going to the end. And when we deployed an environment where these two things came apart, now we can tell. And if it does the wrong thing, it could be really capably doing the wrong thing in this sort of new environment. And so this is one example of a way in which a model can sort of fail to have objective generalization. Its objective can fail to generalize properly, while its capabilities still generalize properly, which is the sort of general sort of subheading under which inner alignment is like trying to address as a problem.
So to summarize, it's good at like at finding green arrows, but it's not good at finding the end of the maze.
Yeah.
Okay.
So that would be a situation where we're like unhappy because it's sort of it's very powerful and knows how to solve mazes properly, but it isn't using those capabilities for the right reason. It's not using them for the one we wanted it to use for. It's using it for this other thing instead.
So yeah, we can say that. I feel like it's somehow similar to people who criticize GPT-3 for not understanding what it's saying, but it's just like repeating and memorizing things. So you could say that GPT-3 doesn't have what we want them to have, which is natural language processing or like human understanding of words and concepts, but just has like memorization. So like he kind of memorized the way of finding the green arrow without understanding the actual task we wanted them to solve. Does it fall into the same category or is it different?
You can certainly think about it that way. I think it's like a little bit tricky to really think about like, in some sense, the like objective of GPT-3 is like predictive accuracy on the next token. It's a little bit hard to understand. What would it actually look like to sort of generalize well or poorly according to that? I mean, it's just like if you have an actual distribution that is similar, I guess in some sense, we only trained it on this web text corpus. And then if we move to some new setting where the underlying generators of the text are different, then, it might still be trying to do predictive accuracy, or you might have learned a bunch of heuristics that are not predictive accuracy. Like what it really learned is it should try to, in any situation, output like coherent sentences or whatever. And then it's like, it doesn't actually try to model the dynamics of this new setting and like get good predictive accuracy. It just, tries to, do the simple, like, well, I learned to do these sort of, heuristics for how good sentences work. And so I'm going to just keep outputting that.
Right. So he found those heuristics. And I think one thing, so there's like two things I remember from Connor's interviews. I'm not sure if it was with me or with other people. One was we don't really know the entropy of human language, of like English. So we don't even know how hard the problem is. So it's very hard to say exactly how successful it is at predicting words or like at understanding it, because we don't have a good model of what English is. And the other one, which is kind of a funny trick, is that I think it took something like one epoch or less than an epoch. So like it only passed through each example once. Maybe I'm wrong. Maybe it took more than one epoch. But it kind of learned to generalize from a few data, just like passing one-shot learning
I
or
think one
something.
epoch is in fact compute optimal in most of these really big language model cases.
So yeah, that's what's something impressive in terms of like, so for people who say like it's memorizing, yes, but maybe, but like from one-shot learning or something. So
Well,
yeah,
I don't think one epoch is very meaningful here. It's just like, well, it got to see every data point
right.
In the training data. And so, it's seen the whole training data distribution. It hasn't seen it multiple times thing is more just our training process just performs better when it can extract, like it's sort of already extracted the information from that data point the first time through, and there's sort of diminishing returns from trying to run it through a second time. And so it's not compute optimal to do so.
Okay, so yeah, so it's okay, so it's less expensive. So like just running it one epoch is enough and compute optimal. And otherwise you would just like lose money because you don't get as much value for your dollar or something.
Yeah.
I'm trying to find yeah the post from Matthew Barnett, because he sent me the code at some point on how to do it. And I'm just trying to put it behind me, because that's a thing I'm trying to do now, putting stuff behind me. So give me just 1 second. So it's mapped with treasures and chests, keys and chests. I don't know if you remember it, then maybe we can talk about it. Otherwise, because I kind of remember some form of this environment, but maybe you also remember it.
Yeah, it's very similar to like my maze example, where it's just like there's a sort of objectives which are indistinguishable on training, and then we move to deployment, and you can see that it like does one and not the other.
Yeah, so if I remember correctly, is like it would stumble on keys, and then because there would be like more keys than chests, so it would open the chest without actually knowing what opening a chest is, and then on bigger environments it wouldn't really know how to do it, or you could still do it in bigger environments. Yeah, something like that. So yeah, if you're a listener, I have some code for it, and there's like concrete problems to demonstrate mesa optimization, or inner alignment failure. Is it an inner alignment failure?
Well, so inner alignment, the way we define it, sort of requires there to be optimization.
Right.
We don't know, especially in the keys versus chest environment where it's so simple, the model probably isn't doing any real optimization internally.
Right. So yeah, I think that's like kind of the problem with calling it optimization, is that we're kind of assuming some form of complexity, or some form of, he's doing some thinking, or some elaborate task, or finding some optimum somewhere of some precise task. So I remember that there was this last long post about a paper from DeepMind about meta learning. So meta reinforcement learning, and it was like top of the alignment forum for a bit, where they showed that it was similar to some kind of misoptimization, and then like some people commented that it was basic reinforcement learning that the thing was doing. It was not some kind of very very special trick. It was just like an LSTM plus some RL, and at the end you froze the weights, and then you get some stuff that can adapt to environments. So yeah, I guess like AI researchers can always say, yeah, GPT-3 is not intelligent. It's just memorizing sentences, or the thing is not optimization. It's just like doing whatever he was trained on to do at the beginning, right?
Well,
just
but there is a truth of the matter. Like, this is an empirical question. So we can look inside of models if we have the good enough transparency tools and discover, how do they work? Are they doing an optimization algorithm? Are they not doing an optimization algorithm? That is something I hope we can eventually do. I don't think we currently are able to quite get there, but I am hoping that we will eventually be able to actually answer these sorts of questions by literally looking inside of our models.
Yep. And yeah, just to close a bit on this, I think that this terminology is super important. So I'm just going to put that back behind me one last time, because I think that's useful for the listeners. So is it in the right side for you now?
Yes.
Yes. Okay. So what we want is alignment, which is kind of what you said about impact alignment, which is AI that doesn't do bad stuff. Then capability robustness is, you can correct me at any time, is the ability to like generalize to harder environments or out of distribution environments. Is this correct? Like you need to be capable enough to generalize well.
Yeah, but it's sort of like generalized according to what is the question. And capability robustness just says generalize according to whatever objective you learn. It isn't saying that you actually learn the correct objective. It's just saying according to whatever objective you learn, you generalize well according to it.
Right. So yeah, you're capable of maximizing that reward, of minimizing this loss in a more general setting than from your training data.
But importantly, capability robustness has no reference to the actual reward. It's not saying according to the actual reward, you generalize well. That's like robustness. Robustness in general says according to the actual reward, you generalize well. Capability robustness is the subset of robustness that says not according to the actual reward, just according to whatever utility function, internal objective, what do I call in the post sort of a behavioral objective, which is just like the objective that actually describes what you're optimizing for in practice. Do you generalize well according to that? Which is just saying, do you sort of just make a bunch of mistakes and not really know what you're doing and don't have anything coherent? Or do you are you coherently trying to do something, regardless of whether that thing is the correct
thing? Okay, cool. So it's okay, generalizing and doing what you were previously trying to achieve in a new setting. And then intent alignment is what we said before as doing what the human wants to do. Like if you say, bring me some tea, bring some tea, assuming he's not killing the baby between you and the tea. Objective robustness is like your objective is robust to what? I forgot.
Well, so it's yeah. So maybe a useful thing also for distinguishing between capability robustness and objective robustness would be there's like another version of this picture where I have it in terms of just like
right.
more
I can take the other one. Is it in below right?
Yeah, there's like the version of the top, which is like how I actually think about it. But then I think if you think about these things in terms of robustness a lot, then like it may be a little bit better to like start from the robustness centric version. They're equivalent. In
cool,
my
yeah, I'm just going to check. Okay, so I'm just going to take the robustness one. How do I do this? Cut. No. Okay, so yeah, I think I'm just going to go to your pros, but you can start explaining if you want.
Yeah, so I was trying to say, so we have robustness. So in the robustness centric version, we split alignment into outer alignment and robustness at the top level, where outer alignment says, is the base objective like doing the right thing? And then robustness says, does it generalize well according to the base objective, which is off distribution, does it continue to pursue the base objective? And then we can split that into objective robustness and capability robustness. And then here, I think the distinction between objective robustness and capability robustness is a little bit
easier.
It's a little bit, yeah, I think it's maybe a little bit easier. So capability robustness is saying, so to make this distinction, we have to introduce in addition. So previously we had the notion of the base objective, which is just like the reward function or the loss function. Then we also introduce the notion of the behavioral objective, which is like what does it appear to be optimizing? And then we say it's capability robust if it's robust according to its behavioral objective. So whatever it looks like it's optimizing, it's like whatever, it does a really good job of optimizing that no matter where it is. So it looks like, if we look at its behavior in general, it looks like it's going to the green arrow. And so we could say its behavioral objective is try to go to the green arrow. That's not what we want. We want it to go to the end of the maze. But when we look at what it's doing, it's clearly trying to go to the green arrow. And then we can ask, how good is it at going to the green arrow? And if it's really good at going to the green arrow, then it's very capability robust, even though it's doing the wrong thing. We didn't want it to go to the green arrow. And so the other part of robustness is objective robustness, which says how closely does that behavioral objective match onto the base objective, which is the one we actually want. And then a sub-problem of objective robustness is inner alignment, which is saying, okay, but what if specifically we have a model which is an optimizer, is running an optimization process, and then therefore it has some objective that that optimization process is optimizing for, which we call the MACE objective. And then we can ask, inner alignment asks, how close is the MACE objective to the base objective? And then the sort of point of both of these diagrams, the sort of overall point is that if we get both inner alignment and outer alignment, then we, and this is the part that's harder to see on this version of the diagram. On the other version of the diagram, it's very clear that inner alignment and outer alignment implies intent alignment, which is like sort of I think a good justification for why it makes sense to sort of split the problem into inner and outer alignment in the situation where your model is a MACE optimizer. That is, it's like doing optimization. If it's not a MACE optimizer, then you can't split it into, you can't sort of, you don't have inner alignment as a sort of concrete phenomenon. You just have objective robustness. And then maybe it makes more sense to look at it from the robustness picture. But I think if you're thinking mostly about MACE optimizers, then you're like inner alignment plus outer alignment gives you intent alignment. Both pictures are equivalent. They're just two different ways of looking at the same.
Yeah, I think for the listeners, the kind of errors are kind of sufficient ways of achieving X. Like if you have robustness and outer alignment, you get alignment, and you don't even need to have inner alignment. Like if we don't have, if there's no MIS optimization going on, and you just have like one optimization process, then you can just have the one optimization process being robust and outer aligned. So those are like sufficient ways of achieving alignment, not necessary ones. Is it correct?
Yeah.
And yeah, and I think yeah, what you were saying is interesting because I've studied inverse reinforcement learning a bit, where the goal is to so you have a human having some behavior, doing some stuff, and you're trying to guess his reward function from his behavior, and his reward function is kind of what he wants to do, and like could be mapped to like some like his values or something of some sort. So if the human was performing optimally according to his reward function, then from his behavior you could infer his reward function. And so this kind of behavioral objective is what an AI would be doing if it was optimizing for the human's objective function, if IRL was tractable in some way, right?
Yes, you can think of the behavioral objective as being related to IRL, inverse reinforcement learning, in the sense that if you did inverse reinforcement learning on some model, then you can think of the objective that you get as a result of doing that as that model's behavioral objective.
Like for any sequence of actions of any mapping from state to action, you can construct a set of optimal policies according to those possible reward functions, right? Or utility functions or reward functions. Yeah. Cool. I think we covered that pretty well. Sorry for explaining basic stuff, but I think most of the audience doesn't know about this paper anyway. Doesn't mean that it's not a very essential one and one of the most important one in the past few years. Just means that my audience is not literate in that. So I think most people. So you talked a bit about transparency and how it's important to solve the AI element problem, and I guess. Chris Olah is one of an important actor in that space. There's other people I met or talked to in the clarity space. I think Nick Camarada, and I think they're like, it takes a lot of time to write a good distill post to explain stuff well, and it's a lot of effort, and it's somehow maybe you get less exposure than like a tweet or something, and but somehow you can say that gaining like understanding of how ML models work is accelerating ML research, and is also giving a good feedback loop between how do we align those. And yeah, I think in your post, you kind of gave both of the arguments and counter arguments from Chris Solo's views, and you're the best proxy, one of the best proxy of Chris Solo's views on that today.
So I think you're referring to the post I wrote, sort of summarizing
Chris Ola's views
Ola's
on AGI safety, I think.
Yeah, so I wrote this a while ago, just sort of after talking with Chris. I think Chris has a lot of interesting stuff to say about AI safety, and I think it's like I don't know, at least at the time, I felt like it was underappreciated and like not really like people weren't engaging with this sort of way of looking at AI safety as much as I wish they were. Um, it's been a while since I've like talked with Chris about this stuff, so I'm like not necessarily up to date on all the stuff with Chris these days.
I think it's from
like
November 2019. So yeah, 1.5 years old, something like that.
Yeah, I think it was like a reasonably accurate sort of like I gave the draft to Chris and a bunch of times sort of going back and forth on trying to get like what does he make sure he agrees with it and stuff. So I think it was like reasonably accurate to like at least a good summary of that sort of stuff he was thinking about then. So yes, I think it's like definitely worth and I definitely think it's Chris is sort of doing a lot of transparency stuff and is like still probably the person who's doing the most stuff in the like space of general transparency stuff that is at least relevant to like AI safety. There's a lot of other people that are also doing exciting stuff like Daniel Filan, other people. Yeah, I'm happy to like talk about any other specific questions about like.
Yeah, so from what I remember from his post was so there was this word in English that I had to Google, which is called mulligan. I don't know if I'm pronouncing it right? Mulligan.
A mulligan.
A mulligan is like a second chance or something. So if we build AI that breaks, or if we build AI that is not something we can correct, that is not like it gives us a chance to correct stuff when we mess up. Being able to like introspect and debug it is instrumentally useful in some way.
So I think that this is sort of one of the arguments that Chris makes for like why interpretability is useful, is it gives you a chance to catch problems before you like deploy your system.
And so yeah, you can catch problems. And there was something about auditing. Let me go back to see what was it. Catching problems with auditing. So yes, we can see if it's not aligned early on, which is very similar to this thing about I forgot the word in English. Yes, the second chance thing. And I think the other, so I think the more like debatable thing is whether is it worse or not the acceleration in ML understanding, is it worse the gains in AI safety? So I think he says that it's worth looking into it. And like I feel like I don't know how much we've gained from learning at Inception or ResNet, embeddings. So I don't think ML researchers are much more competent from looking at these, but I'm also not sure how better AI safety researchers are. So yeah, I'm not so sure about the trade-off right now, but maybe in the future it's very important to be able to debug it. So yeah, I don't know what do you think are the upsides and downsides, if you remember?
Yeah, so I can sort of talk about my views. Sure. I think my sort of perspective on transparency is that we sort of need to be able to train models in such a way that doesn't just look at the model's behavior. So I think Chris has this view, like with catching problems via auditing, where he's like, well, we train some model and then we can check to see if we did a good job with transparency tools. And I think I have a somewhat different view, which is we don't want to use transparency tools to check after the fact. We have to use transparency tools to solve the problem in the first place. Because if we just try to train models to do the right thing via like behaviorally making sure they look like they're doing the right thing, we can end up with models that aren't actually doing the right thing and are just pretending to do the right thing. And the only way to eliminate models that are pretending to do the right thing is via looking inside of the models internally and training on, is the model actually trying to do the right thing, not just sort of looking like it's doing the right thing. And so I'm sort of in favor of approaches where we directly train models to sort of using transparency tools. Whereas I think Chris is sort of more in favor of trying to use transparency tools as a way to check behavior as a sort of independent check after we have attempted to train a state model using some other approach.
Right. So you're more like interested in kind of looking at it while you're building it, so you're not like doing something like misoptimization or bad things or deceptive behaviors. Whereas Chris is like more like in a postmortem. You see why it didn't work.
Yeah.
So yeah, I think the yeah, I think this diagram I have behind me, I hope it's the right way for everyone. So we start from some kind of model. So in the y-axis is how interpretable the thing are, and on the x-axis is how strong or like capable the AI is. So at the beginning, you understand what it's doing, then you start doing something like MNIST, handwritten digit recognition. You don't understand the neurons because they're not expressive enough, or maybe you have some understanding, but not, you're a bit confused. Or like those big models like Inception, ResNet, or Transformers are a bit more abstract. And then when you get to something, and then what we're trying to, what we're learning is when you look at latent path from GANs or transformers, we're saying something close to knowledge, and we're more and more understanding because it's more and more expressive, right? And at the end, when it's becoming superhuman, then it's very hard for humans to understand because it's like super optimized in a totally different language.
Yeah.
And so it's useful to do interpretability to be like in this crisp abstraction way of understanding AI when it's still like kind of human level or before human level somehow. Like it doesn't go alien before it goes human level. So we have some time.
Yeah, so I have some belief that we can probably just avoid the drop off at the end if we use an amplified overseer to do transparency. So this is obviously, you know,
an oversight overseer. What do you say?
An amplified overseer.
Oh, amplified overseer. Yeah, yes, yeah. So I think that is like most of your proposals later. Well, I think this will be like the last part of the podcast, the last 20 minutes. It's just like your like 11 takes on how to like combine kind of amplification, overseer, and interpretability. But there was like a little point that I found interesting in case of like field building. So now both of us are trying to do some field building in AI alignment, and Chris Ola is maybe more thinking about field building in the interpretability space. And so you think like I think if I remember correctly, the two arguments that make it attractive for researchers, one is if researchers are in a lab at university, they can still do interpretability research without having billions of dollars to spend. They can just look at neural networks and make it understandable. And I think one of the assumption he has is that there are like some low-hanging fruits in doing interpretability research now, because not many people, it's like pretty neglected, or at least it was in 2019.
Yeah, I definitely think, yes, this is something Chris has certainly worked on. Like the point of Distill is to try to get like, you know, interpretability research more like, get more attention and more prestigious and like more cool from a
and I think he succeeded. Like the post about, I think it was CoinRun, where you visualize how you visualize features in CoinRun and how you map the reward. That's pretty cool. I think the microscope, microscope from OpenAI, where you see the features of all those like learning models, was pretty cool. I don't know if you've done some representation from Clip. I think Clip was, yeah, I think Clip was his own like pictures. He didn't use me a microscope. I'm not sure. And yeah, and I think that there's like another argument, which is you're trying, so if you're forcing your models to be interpretable, it's a good analogy would be forcing your students to show that that they've done good work. So show their papers or show their process. So they're not good-hearting the actual optimization, but they like showing everything. So they cannot. It's harder for them to lie if they're transparent, explicitly transparent.
Yeah, I think that's sort of closer to the sort of thing I was talking about, where I want to use transparency sort of as a training.
Yeah, maybe not Chris, maybe like more you on these posts.
Well, Chris also is like interested in this, but it's not his like primary motivation.
Right. So yeah, maybe let's talk about your stuff. So I think your most important post on okay, in my opinion, on the A11 forum or Let's Wrong was 11 proposals, an overview of 11 proposals for building safe advanced AI. And you have 11, so maybe we can, like, I think like there are like 5 or something key points, which is transparency, over amplification, imitation, amplification, and then there's something like adversarial training, and then you kind of combine the 3 with microscope, STEM AI, reward modeling. Yeah, you have like 5 or 6 teams that you combine. You can think about, maybe we can start with the first one, which is the one that talks about amplification. I can put the slide behind me.
Yes, there's 11 proposals. So the second one is the first one that is about amplification.
All right.
And it talks about imitative amplification, which is a specific sort of form of amplification where, very simply, we train a model on the objective of imitating a human consulting that model. And so I have a bunch of these different proposals. They're not unique to me. I try to sort of take a bunch of proposals throughout the literature, and then I try to compare them. I think the sort of main thing that this post does is it's comparing all of these proposals on 4 axes, where these sorts of axes are outer alignment and inner alignment, which we talked about, and then training competitiveness and performance competitiveness. Where training competitiveness is how hard is it to train, and performance competitiveness is if we do train it, how good is it? And so all of these sorts of four conditions are the sort of central things that we need if we want to be able to have a sort of competitive and aligned procedure for building artificial intelligence. And so, we can look at all these different things that people have talked about and like try to address. Do they satisfy these sorts of things? I think the general answer is, well, it's unclear. But certainly for none of these proposals, we don't have a really strong case that they definitely do. But certainly it seems like, we can say some are more promising, some are less promising, but that's going to depend on like, your particular research case. I'm happy to talk about any of the particular proposals and like,
so I think there's like more than just like, we can talk a lot about will it work or not, but then there's like, is there any concrete feedback loop that will tell us if something works or not? Or is there like any empirical environments or research that can give us feedback? So I feel like the whole like debate to like amplification work from Paul was pretty empirical, whereas so most of the stuff you post is empirical, but some of them are maybe more easier to test. So in the next years, I don't know about amplification because that would require some kind of recursive loop or yeah, I don't know where we are in terms of trying to do IDA empirically. But yeah, maybe just basically, I think so the first proposal was somehow doing multi-agent safety with a bunch of agents, like the cooperative hide and seek from OpenAI. And the second one is about imitation amplification. So maybe you can explain a bit what is going on here with the H and M, A and Q, which I think is one of the most interesting and useful to think about the other ones.
Yeah, so what you have there is on the second proposal, which is about imitative amplification, which is describing how imitative amplification works. So imitative amplification, you have a sort of, you first need to find the amplification operator, which takes in some model M and produces a more powerful version of M. And the way it does that is it says we have some human which consults multiple copies of M to produce an answer to some question. And then this process of a human consulting M is what we refer to as the amplified M. So this amplification operator applied to M produces a more powerful version of M, which is a human with access to that. Now you can implement this amplification operator in different ways. In imitative amplification, this is how we implement it.
And yeah, we can go back to our example of Sundar Pichai having 5 AIs helping him do stuff. I don't know if it's a good example, but it's like kind of amplified by AIs. But because I think one important thing is that in the case of amplification, you can get more intelligence from 10 agents than from let's say 1, and then but 10 agents will be less able to take over the world because there will be like you could kind of control them, right? So it's easy to see like each individual ones are aligned, but like each M is aligned, but then the sum of them are smaller than just one M. Is that basically the intuition, or?
Yeah, it's complicated. Like, why do we think amplification actually produces better models? I mean, so I think that, like, you know, at least in imitative amplification, we have this argument about HCH, where it can be like, in the limit, it converges to an infinite tree of humans consulting humans. And then there's, arguments we can make for like, it seems like this is a reasonable sort of idealized reflection process. And so, it seems like a good thing to trust.
Oh, is it? Oh, is it like humans consulting HCH? The thing you're saying?
HCH is a recursive acronym which stands for humans consulting HCH.
Okay, okay, right. So yeah, then this is like I can infinite loop, and then you have different ways of doing amplification by approval, by different training, directly training on something. And let me see if I have other ones which were interesting. I think one of the funniest one is the one about STEM. So you basically tell the AI stop thinking about humans, just think about science. This is like a very bad summary. This is a straw man, but this is what I got from just like reading the first paragraph, I guess. Is that the proposal?
So AI is a proposal where we're like, well, it seems kind of dangerous to train models in environments where they have access to a bunch of information about humans. Maybe we can just get away with training models in environments where they only have access to information on math or something, or science or technology or whatever, and then we just use that. And then the problem with this obviously is that, well, you can't use it for a lot of things. Like it doesn't, you can't use it for like geopolitics or running a company or like anything that would involve human modeling, but you can still use it for a lot of things. And so maybe it's enough, though maybe not.
Yeah, I think if we have a very good AI that maybe it's from Robin Hanson, but it's like you have this advanced like super accelerated human civilization in your computer, like brain emulation, and it runs for like billions of years or 1,000 years, and at the end it produces some output of like all the research he has found over the years. So if we have some kind of oracle AI that is very good at science, you would get like all those insights about science without having the problems of it trying to find our values or something. But then we would still need to have some kind of boxing problem for it to not escape and make the Earth a penetrate or something. But yeah, I think it's a good objective to be good at science. I think the other ones are about debate or amplification, and there's also one. I think one thing that is interesting me is real-world modeling. So I think like DeepMind as at least used to have this different approach. So Chai, Center of Human Compatible AI at Berkeley, who do inverse reinforcement learning, trying to find a Warren function, whereas DeepMind AI safety team was mostly trying to do reward modeling. And I don't fully understand the difference. And how it in your blog post, you give some solutions with reward modeling. So if you could explain that to me, that would be like helpful on a personal level.
Yeah, so here's how I think about recursive word modeling. So in imitative amplification, we have this amplification operator, amp-m, where we just have a human consulting the model, and this is how we produce a more powerful version of the model. In recursive reward modeling, we have this sort of a new version of the amplification operator, where now what the amplification operator does is it does the following thing. It trains a reward model on the sort of humans like feedback. It then trains an agent to optimize that reward model. And then it gives the human the opportunity to look at what that agent does and give additional feedback to refine the agent. And then once this sort of converges, the human is given a lot of feedback and trying an agent, which is like, we found a reward model and we found an agent, which is, in fact, trying to do the sort of optimize for this reward that the human is trying to give feedback for. Then we call the resulting agent the sort of amplified version of the original model. And so we have this new amplification operator, which does this whole reward modeling process. And then we just do sort of standard iterated amplification on top of that new amplification operator.
But what's the difference? Maybe it's a layman question, but what's the difference between trying to infer like deep RL from human preferences, like human saying yes or no, like trying to tell the AI, like cooperative IRL, where you're trying to have a human say what is the correct behavior, and reward modeling, like you basically have a human in the loop saying what he wants to do, and a reward model, which is kind of a reward function. Is a reward model a reward function? Or is it different?
Well, reward model is not, it's not a reward function because we learn it. So a reward model is a learned model.
Right. So it's like a model. Well, when you're trying to do IRL, you also have like a model of the reward function. So you have parameters that define your reward, right? It seems to me very similar, but maybe I'm missing something.
Well, it's similar to IRL, but it's not quite, because we also train an agent to then optimize for that reward function, and then we also refine the reward function by letting the human look at what that agent does.
Right. Okay. Cool. And yeah, I think the last paper that I think was kind of interesting in terms of AI alignment was where I'm also having trouble understanding is learning to summarize from human feedback, where there is this kind of human feedback where I think the AI does summaries, and the human says what summaries are good or not. And so there's a mixture of kind of RL and NLP, and at the end there's like human feedback in the loop. I don't know if you can give a good explanation on that. Otherwise, like, I can read it on my own. I think there's like a similar diagram to it. Let me find it.
Yeah, they're certainly doing something similar. I think it's a little bit simpler. They're just saying, we learn like, well, it's actually very similar, because they're learning a, I don't know if it actually goes through the step of having a reward model though. I think what it does is it just learns an agent, and then the human gets to look at the agent's actions and then give some preferences, and then you refine the agent based on the human's preferences after looking at the agent's behavior. So it's sort of similar, but skips the step where you train a separate reward model. At least if I'm remembering the paper correctly.
Yeah, I'm just trying to find I think I have the thing, but I'm not sure. One sec. Save as. Right, I think they're giving me an SVG image, which is a bit hard. Okay, but yeah, let's not go into this paper if we haven't looked both at it. Anyway, do you have okay? Let me. This is my closing question. What is the most underappreciated subproblem of AI alignment you would want people to work more on?
So this is a little bit of a weird question because it depends, I think, very heavily on who I'm giving the advice to. So like there's the problems that I work on, which obviously I'm working on them because I think they're the most important things to work on, which are things like myopia, and how do we sort of understand what it would be,
What's
what it would look
myopia?
like. Sort of how do we understand what it would look like for an agent to sort of only care about a sort of single action and not optimize for anything else. I think this is exciting, but it's not necessarily something I would want like I don't know. I think it's like complicated and it's like, I don't know. I think if you wanted to work on this or something, the right thing to do is just like talk to me a bunch. Whereas like I would say the more general advice, if I want to just like, if you're trying to get into AI safety and I don't know, you have some machine learning experience and just want to do something, I think that the like my current advice is like try to do transparency and interpretability research, sort of like in the style of like circuit style stuff.
So yeah, you're referring to like your post on or Pulp Fiction post on circuits, right?
No.
No, or Chris Ola's work on circuits.
Yes, I'm referring to Chris Ola's work on circuits.
Right. Cool. And yeah, maybe I think it's hard for people to actually give precise answers to that. But do you have are your timelines aligned with kind of AGI Code Stress report on AI? I don't know if you've read this.
I have a very high degree of uncertainty on AI timelines that
yeah.
I don't think is very resolvable.
It's hard to talk about it publicly. But I would.
No, it's not that it's hard to talk about it publicly. I have a high degree of uncertainty. I do not know what the correct AI timelines are. And in fact, I think that it's very, very difficult in practice to estimate good AI timelines. And so I think Ajaya has done an admirable job. And if I had to like pick a number, like as a modal guess, probably I would pick Ajaya's number, but like I don't actually put very much stake in any particular analysis of like how long things are going to take, because I think it's very, very difficult to predict these sorts of things.
You can say that she did a very good job and it was very rigorous. It was before something like DALL-E came. So I think most people I've talked to in the ML space kind of updated a lot on DALL-E as, or Clip at least, as like multimodal and being able to like understand concepts as doing an avocado share or something. And when I look at a bunch of our stuff on Eleuther AI Discord, I'm kind of amazed at like how good it is at understanding kind of concepts. Like even if you have like very conservative timelines and like being very uncertain, I think have you updated on DALL-E or not? That's my question. That's my real last question.
I don't think it's that big of an update, I guess. I feel like, I don't know, like starting from like GPT-2, and even from like BERT, I don't know. We've seen really impressive feats from language models going far back now, I think at this point. I think like, I guess I feel like you shouldn't have been that surprised that like it also works to like say things in multimodal settings. Like it just feels like that's the obvious thing that's gonna happen next. I guess like I didn't feel like Clip or DALL-E was like extremely surprising, I guess.
Yeah, what would be something that would surprise you?
What would be something that would surprise me? I don't know. I mean, lots of things would surprise me, I guess. In like hindsight, what are things that were like surprising to me? Well, like I said, I definitely think the success of like transformer-based language models was surprising. I definitely think that I think that like AlphaGo was somewhat surprising. I don't know,
big stuff. Okay, cool. Yeah,
everything's surprising, right?
So
to some extent, but like,
I think, go ahead.
No, nothing.
Oh yeah, Transformers. Yeah, Transformers were surprising, and according to Connor, there's like this hypothesis that Transformers is all you need. He didn't say that, but that's like a meme of like, if Transformers is all you need for AGI, then maybe we did the most important part of it, and then like plugging RL into it is the easy part.
It's the very strong version of attention is all you need. Attention is really all you ever need.
Yeah, is all you will ever need. So if it's right, then we don't need, you will never be surprised, and you will just Transformers enough. anyhow, I won't take you more of your time. It's 2 a.m. at my place. It was very good to have you.